Hello, I'm Mrs. Quint, and today I'm going to go through with you how to change fractions into decimals. Okay, so here we have the fraction 5/8. We're going to talk about changing that into a decimal. Now the first thing you have to understand about fractions, which you probably already understand being in 8th grade, is that the numerator represents how many you want, what you're dividing into. And the denominator represents how many you're dividing by. So we're taking 5 and we're going to split it up into 8 parts. Now, as you can probably already imagine, if you take 5 wholes and you split it up into 8 parts, each part is going to be less than 1, right? Because 8 is greater than 5. So we're going to expect a quotient, right? A quotient is the answer to a division problem. We're going to expect the quotient to be less than 1. So if it's not, we know we've done something wrong. All right. So in order to do this with long division, I'm sure you've seen this before, 8 goes on the outside, 5 goes on the inside, okay? And 8 goes into 5 0 times. Now remember, that is what we expected. We expect this to be less than 1. So this is all fine. 0 times 8 is 0. We have 5 as a remainder. Now, I'm going to do a trick here, which is add the decimal expansion of 5, right? Not adding any value to 5. I'm just adding some zeros in here. So now what I can do is I can put a decimal here and pretend as if this number is 50 instead of 5.0. 8 goes into 50 6 times. That would be 48 with 2 as a remainder. Oops. I want to bring down a 0 here. And then I can say 8 goes into 20 twice. So we have 16 and we have 4 as a remainder. Bring down that final 0. And 8 goes into 40 5 times, and that is actually going to be the end. This was a terminating decimal, it's called. So 5/8 is equal to 0.2625. Now remember that this makes sense in a lot of ways because 8 is greater than 5, so we have no value here in the ones place. We know that 5 is greater than 4, so 4/8 is 1/2. If it were 4/8, it would be 0.5. Since it's 5/8, it's 0.625. So this is greater than 1/2 is what I'm trying to say. So just take a second once you've done this to sort of run it through your head to make sure it makes sense, because doing that process will eliminate a lot of the mistakes, a lot of errors in your work. Okay, so this number right here, we're going to take the 2 and we are going to divide it by 9. Now, 9 goes into 2 0 times, so we're going to have to do this trick again. So 0 times 9 is 0. We'd have 2 as a remainder. We bring down the 0. Whoops, it's a little too eager about putting the 0 in here. That's not a 0. So we have right here, 9 times 0 is 0. Bring down the 2, bring down the 0. 9 goes into 20 twice, so that's going to be 18. So we bring down the 2, we add another 0, bring that down. 9 goes into 20, but we just had a 20, that's okay. Okay, I'll just put a 2 here. This goes into 18. Okay, I'm beginning to see a pattern here, which is that every time I get a 20, which means 9 goes into 20 the same amount of times, I get a 2 as a remainder. This process of getting 20, subtracting 18 from it, getting 20, subtracting 18 from it is going to continue to go on. Right? So I'm going to continue to have the same pattern in my quotient because my remainders continue to be the same. So what happens here? We have 2/9 is equal to this number 0.222. Well, how do I write this? Well, there's a couple different ways I can write it. I can use these 3 dots here, which means that the pattern that I've established, which is the 2's here, continue. These are called ellipses, right? You see them a lot of times in ELA, actually. You can also write it, I think I like better to write it with bar notation. So you write down the number that's repeating, which is 2 for us, only one number repeats, and you write a bar over it, okay? And this is called bar notation, right? So we're using bars to represent repeated decimals here. You could also have written, 0.22 with a bar over, because repeating 22 is the same thing as repeating 2. I prefer to just write however many numbers are repeating with that bar. So I prefer not to write this, but to write this is, it's a little shorter to do that. Okay. All right. So two different ways you can write it. I prefer bar notation, and I prefer to only write as many numbers as I need to. Okay. So you've already been introduced to two different types of decimals. This one right here terminates, it finishes, it stops, and this one here repeats. Now I say that it stops, but the truth of the matter is that I could keep adding zeros here to the right, but we don't call adding zeros here, since we're not adding value, we say that this terminates because the values in the decimal place terminate. I could add zeros, but that's not really adding value, whereas this one has a 2 that keeps repeating itself, so this one continues to add value in its decimal expansion. Okay, let's check out an improper fraction. So this is an improper fraction because the numerator is greater than the denominator. When this happens, we would expect the quotient to be greater than 1. Okay, and so here I already see that 5 goes into 8 once, so I already see that it's going to be greater than 1. Put the decimal up here, 5 goes into 36 times, and this is also then a terminating decimal. This is 1.6. Okay. Finally, another example where we have a mixed number. What I want you to remember about a mixed number is that it is the whole part plus the fraction part. That's what a mixed number does. So the long way of converting this is to put 3 over 1, and then to convert 3 into something over 7, which would be 21/7. We'd multiply it by 7 over 7, and let's just show that process here, because we have to have common denominators when you're adding fractions. And then here we just add the numerators together and keep the denominator, 26/7. So you might have seen this shortcut where you multiply the denominator by the whole number, and then you add that, whatever the product is, you add 5 to it. You add the numerator to it. So 3 times 7 plus 5, and then what you do is you keep the old denominator, so this actually just gets you 21/7. And what this process is mimicking the long way around, where you put 3 over 1, you get 21/7 because it has a common denominator, and then you add the 21 to the 5 to get 26. So it's kind of a nice little shortcut to circumvent this long way around. Now let's pretend like we had a negative here. Now what you would do for negative is, if you have a negative mixed number, what you don't want to do is use it in your shortcut here, or use it like this. You sort of want to disregard the negative until you're all finished, and then in the end you want to add the negative to the fraction. If you did it like this, you would get negative 21 plus 5, and that gets you negative 24. Now you know that that's not going to be the answer here, because the answer is actually just going to be the opposite of whatever 3 and 5/7 is, right? So it's going to be negative 27 and 26/7, because if you took this away, this just means the opposite of this mixed number. So I can't get a negative 24 because I know the numerator is negative 26. So it turns out you got to be very careful of this shortcut, because if you have a negative, you have to sort of disregard the negative for a minute, use your shortcut, get 26, and then you can add the negative in the numerator. You can even add it in the denominator if you want, which is pretty rare. You don't really see that often, but you could if you wanted to. It's not the most convenient, but you could do numerator, you could do denominator, or you could add it so that it's at the same level as the fraction bar. Okay, I often prefer either the numerator or the same level as the fraction bar. This is really rarely used, but it's equivalent. Okay, so what you might have noticed, or what you might be asking yourself if you were curious, is why are some fractions terminator and why are some of them repeating? Because it seemed kind of arbitrary. We had 5/8, which was 0.625. We said that was terminating, and then we had 2/9, which was repeating. So what makes this repeat and this terminate, and how are we going to be able to tell? Because fractions either terminate or they keep repeating their pattern, right? Something that doesn't terminate and doesn't repeat can't be represented as a fraction. It's called an irrational number. We're going to go over that later. So what is the difference between this fraction, and are we going to be able to tell? So let's say that we take a fraction. Let's say that we take the fraction 4 over 28. Without using a calculator, how am I going to know if that terminates or repeats? Well, the first thing you want to do if you get a fraction like this is you want to reduce it. So this trick only works if the fraction is reduced. So 4 and 28 share a factor of 4. 4 divided by 4 is 1. 28 divided by 4 is 7. Okay, so we have it reduced. Now the trick is that the denominator can only consist of 2's and 5's. Okay, so the trick is that the denominators can only have 2's and 5 when it's prime factors in its prime factorization. All 2's are okay and all 5's are okay, and both 2's and 5's are also okay. And there's a little asterisk here, which is that must first be reduced. So we reduced 4 over 28 to 1/7. Now 7's prime factorization is just 7, so it doesn't have 2 or 5 in it, and certainly doesn't have 2 and 5 in it. So here we know this is going to be repeating. Okay, this is the trick to show that it's terminating. Okay. So if we took another number, like let's say that we took 36. Okay, so let's say that we have 5 over 36. This is already reduced. 5 and 36 don't share a common factor. Let's look at the prime factorization of 36. 36 is 4 times 9, which is 4 is 2 times 2, and 9 is 3 times 3. So right here, these 3's, the fact that they're present here makes it a big problem, because it's not just 2's or 5's or both 2's and 5's. So this right here is going to be repeating. It's not going to terminate. Okay, that has everything to do with our base 10 system. Our base 10 system, the prime factorization of 10 is 2, and 10 is 2 times 5. So since it's 2 and 5, we know that something that terminates is only going to have 2's and 5's in it. There's a trick to get them so that we can represent them over powers of 10. Once they're represented over powers of 10, then they'll terminate. Okay, so just remember, this is the reduce it, find its prime factorization for the denominator, and then you know if it's terminating or repeating. And that's it. That's all. All right, see you next time.